Okay guys, welcome back to Econ, and let's continue again our discussion on consumer theory. In the last three videos, we have covered some primitive notions, preference relation and types of preference relation and axioms of choice. And now let's begin our discussion on utility function and one of the most important theorem in consumer theory, which is the representation theory. How we can represent preference relation using utility function. So let's jump up. So first of all, let's cover utility function. What is utility function and what it can cover? So as a very easy definition, utility function is a mapping of consumption set into real numbers. And this mapping summarizes and represents the preference of a consumer in an ordinal fashion. Or in another way, we can define utility function by using this definition. A real valued function of u that we can map from consumption set to real numbers is called the utility function representing preference relation f for every x and y bundles in consumption set. X is at least as good as y if and only if the utility that you receive from x is at least as much as the utility that you receive from y. And recall that in the previous videos we said that basically we say that the consumption set is equal to the RL plus L-dimensional non-negative real numbers. So that's why instead of x capital X, which shows the consumption set, we simply can write down utility function is a mapping of RL plus into R. So either you write from X to R or RL plus to R, both of them is the same. So now let's talk about representation theorem and let's prove that preference relation can be represented by utility function. Or another way we can represent preference relation by using utility function. If preference relation on consumption set, which is equal to RL plus, or rational, that means it's complete, transitive, and reflexive, and it satisfies the axioms of continuous and strictly monotonic, then there exists a continuous utility function ux that represents the preference relation. Or we can say utility function is a mathematical function that denotes the satisfaction derived by people by consuming a bundle of goods. So now, based on the representation theorem, we are going to find out that we can represent this preference relation by using a continuous utility function. What we are going to prove that? We are going to prove that that preference relation can be represented by a continuous utility function. Let's work on that. So what we are going to prove? We are going to prove that let the preference relation be rational, continuous, and strictly monotonic. It should satisfy the sets of rational axioms, which is reflexive, which is complete, which is transitive. And also it should be continuous and it should be strictly monotonic. And let we have a vector of E. Let we have a vector of E that is a vector of ones in RL plus. And consider the mapping of a U function from an L-dimensional non-negative real numbers to real numbers defined so that the following condition is satisfied. So suppose that we have some ux that we can multiply by E, the vector of ones, as indifference to a consumption bundle X. So maybe there will be one question raised. Why we need this vector of E, which is a combination of different, which is a combination of ones, just a vector of ones. So therefore, let's understand first what this relationship ux multiplied by EE as indifference to x means then. So let us first make sure we understand what this says and how it works. In words, this relationship says that take any x in domain of RL plus and assign to it the number ux such that the bundle ux multiplied by E with ux unit of every commodity is ranked indifference to x. There's a number ux and we have a bundle of ux multiplied by E with ux unit of every commodity is ranked indifference to x. So the question is why we need E or vector of ones here, because ux is a real valued function and commodity bundle is a vector. So we cannot directly compare a real valued function with a commodity bundle which is vector. That's why we need to multiply this real valued function with a vector of ones, which is E here, in order to change this side also to a vector unit. So now we can compare this vector unit, which is ux multiplied by E, to this vector, which is x. So that's why if you see this graph, for example, we pick up this ux multiplied by E, which this ux multiplied by E, which is here, just right around here, it's indifference to x. It's indifference to x that we can pick up some numbers from ux here from x dimension and ux here from x2 dimension, and we compare this ux that's here just in the cross point of this 45-degree line with the indifference curve that the x bundle is located there. So that's why ux multiplied by E is indifference to this x. So this is what it means, this relationship. And now let's talk about some other things. Let's suppose that for a given consumption bundle of x, that is which indifference with the ux multiplied by E, the restricted upper contour set, which is we denote here by bx, which is like a set of t in R such that t multiplied by E is at least as good as x, this set be a restricted upper contour set, and also let that the wx, which is also a set of t in real numbers such that x is at least as good as this te, be restricted lower contour set. Now let's talk again with using this curve or this graph. When we think about the upper contour set here, this is the upper contour set. Like the above values are the above location of this indifference curve, or the curve of x. This is upper contour set, which is at least as good as this x, and also we have some restricted lower contour set here, which then the x is at least as good as those lower contour set. So, and also by a strong monotonicity, bx, which is the upper contour set, is non-empty. Why? Because by strong monotonicity, we say that more is better than less. It means anything that we have in this upper contour set, it's non-empty, and they are better than x bundle. This is what strong monotonicity says. When we say that t multiplied by E is at least as good as x, it means they are weakly preferred to x. By strong monotonicity, this upper contour set should be non-empty. And also wx, which is the restricted lower contour set, it should be also non-empty, since 0 included here. If there's nothing else, at least 0 is included here, because maybe you can compare the x bundle with something that there's nothing, there's just 0 amount of any commodity that we have. And also, by the axiom of continuity, upper contour set and also lower contour set are both closed. And it takes the boundary is also contained in this set. It includes the boundary. And also by completeness, the set, upper contour set, and union of upper contour set with the lower contour set is equal to the real value. Because this lower contour set take the value, any value less than the curve or the graph that x is located here. Any value that lower than this x or the lower contour set, and any value upper than x or the upper contour set. So if we combine both of them, it should be equal to that real numbers. And by connectedness of real numbers, there exists such a tx in R such that tx multiplied by e is indifference to x. There exists a tx in real numbers such that tx multiplied by e is indifference to x. Again, tx is some number which is in a set of real numbers. And if we multiply that tx by e, also it's changed to a vector, then we can compare it to another vector which is x. So then this tx multiplied by e is indifference to x. So now, again, let's go back to the definition of utility function. Now here, as we know, here, ux multiplied by e is indifference to x. And also here we have tx multiplied by e is indifference to x. Then what we are going to do, it means this e is equal to this e, this x is equal to this x. Only when e is equal to e and x is equal to x, then ux should be equal to tx. That's why here when we define the utility function, then ux should be equal to tx. So now we claim that the utility function of u represents the preference relation. In other words, giving an x bundle and consumption set and y bundle and consumption set, then utility of y is greater than and equal to the utility of x if and only if y is at least as good as x. Or we can say the utility of y is at least as much as the utility of x if and only if the bundle y is at least as good as the bundle x. So when we say if and only if, it means that both sufficiency and also necessity conditions should be satisfied. So now we are going to prove that this relationship exists. We are going to prove that we can represent this preference relation that y is at least as good as x can be represented by a utility function. If and only if the utility of y is greater than and equal to the utility of x. So first of all, we need to prove that the necessity and also the sufficiency condition can be satisfied by this relationship. So let's go prove first the sufficiency condition. Assume that the utility that you receive from y is at least as much as the utility that you receive from x. And also by the definition of the utility function in this slide, we said that ux is equal to tx. When ux is equal to tx, then the uy is equal to ty. Then instead of uy, we can simply write down ty, and instead of tx, we can simply write down, instead of ux, we can simply write down tx. So then, when uy is at least as much as ux, then their value, which is ty and tx, then ty is at least as much as tx. And by strong monotonicity, now when we multiply ty with e and tx with e, then we change them to bundle of commodities. And by strong monotonicity, we say that more is better. More is better. It means we prefer more of a good than less of a good. Then ty, when we multiply it by e, it should be preferred than the bundle of tx multiplied by e. Then ty multiplied by e is at least as good as tx multiplied by e. Why? Because ty is greater than and equal to tx. Then when ty is greater than and equal to tx, then ty multiplied by e should be weakly preferred than tx multiplied by e. That's what strong monotonicity says us. And by definition of the utility function that we previously talked about, that here that ux multiplied by e is indifference to x. And now when ux is equal to tx and uy is equal to ty, then ty multiplied by e should be indifference to y, and tx multiplied by e should be indifference to x. Should be indifference to x. So now we can substitute this ty multiplied by e and ty multiplied by tx multiplied by e to this relationship that we withdraw by the strong monotonicity. So now just simply instead of ty multiplied by e, which is this one is indifference to y, we just simply substitute it, and instead of ty multiplied by e we can write the y, because what we derive from the definition of utility function that we already provided. And instead of tx multiplied by e, which is like this, tx multiplied by e is equal to ux multiplied by e, and ux multiplied by e is indifference to x, we can just simply substitute this tx multiplied by e to x. Then finally, by the transitivity, when y is equal to ty multiplied by e and tx is indifference to x, then instead of ty multiplied by e we can write down y, and instead of tx multiplied by e we can write down x, and we substitute y to ty multiplied by e in this relationship of strong monotonicity, and we substitute x instead of tx multiplied by e in strong monotonicity, and just we will have this relationship by transitivity, which is y is at least as good as x. So then when the utility of y is greater than and equal to the utility of x only if y is weakly preferred to x, or y is at least as good as x. This is the proof of sufficiency here. And now let's prove the necessity condition of that relationship. Now assume that y is at least as good as x. Then by the definition, ty and tx, now we have the ty multiplied by e, which we can take it from the previous relationship that we already talked that, because ty multiplied by e is uy multiplied by e, or the utility of y multiplied by e, and tx multiplied by e is the utility of x multiplied by e. So instead of uy multiplied by e we can write down ty multiplied by e, and instead of ux multiplied by e we can write down tx multiplied by e. Then ty multiplied by e is indifference to y, and tx multiplied by e is indifference to x. Again by transitivity, and instead of y and x in this weak preference relationship, we can write down, instead of y we can write down ty multiplied by e, and instead of x we can write down tx multiplied by e. Then ty multiplied by e is at least as good as tx multiplied by e. Just we simply substitute this relationship into this assume that y is at least as good as x. So then by strong monotonicity, when ty multiplied by e is at least as good as tx multiplied by e, then ty should be greater than and equal to tx. Because when the ty multiplied by e is at least as good as tx multiplied by e, then by strong monotonicity, ty should be at least as much as tx. And finally, by the definition, we know that ty is equal to uy and tx is equal to ux. Then we also prove the definition of, or the condition of necessity in this utility function, that y is at least as good as x if utility of y is greater than and equal to utility of x. So now we prove both. Then we can say that uy is greater than and equal to ux, and if and only if y is weakly preferred to x. Or we can say another way, the utility that we receive from y is at least as much as the utility that we receive from x, if and only if y is at least as good as x. But now, another thing that we are going to talk about in the representation theorem, which is the final step, is to prove the continuity of the utility function. This is the final step of the representation theorem.